So if I redraw the spectrum, where let's say we have FLO here, and instead of showing the entire band, let me just show you one channel which we are trying to down convert, and later on to pass it through the channel selection filter. So this is FRF. So this is the desired signal which we want to mix and bring it to a lower frequency. So we can see that this difference frequency, which is your FIF, is equal to FRF minus FLO, will result in signal to appear here. So here we are showing only the single-sided spectrum. This mixing operation is going to reduce the frequency of the input signal to FIF. And since this mixing operation does not only the frequency down conversion, it also increases it also results in some of the frequencies of the input signal. We will be also getting a component at FLO plus FRF. But right now we are just ignoring because that is not going to pass through the channel select filter. So let's say we have a channel select filter here. Now, important thing to notice here is that there will be possibility of another signal to be present at an FIF spacing lower than FLO, because there can be signal, we can just assume that presented the entire band, let's say. So even though the channel select filter is going to select our desired signal, but we also have the signal which may be present. Okay. See, let's FLO minus FIF. So if we have a frequency, some signal which is presented at this frequency FLO minus FIF, now this LO can mix with this signal at a lower frequency also, and cause it to appear at the same FIF frequency as that of what we wanted for our desired signal to appear. Because this spacing is same as the spacing for this undesired signal. This is your desired whereas this guy is undesired signal. What is the issue? Already we can see that if this signal which is not desired is comparable or stronger than the desired signal, then even though we have a channel select filter present, it is not going to differentiate between the two down converted components. So we will be losing complete information and there is no way to retrieve this information. So this component, which is at the same FIF distance from the halo as our FRF, is also called as image signal because it looks like a mirror image of FRF about the halo frequency. This is called as image signal. This frequency, FLO minus FIF, is also called as image frequency. Here we can easily see that this image is going to directly interfere with our desired signal after down conversion. We just saw the problem of image. Now we are going to see some possible ways to solve this problem. Problem of image signal. So to understand, let me just redraw again the spectrum. If you remember, we had discussed about this part that we need to add a band select filter to select the desired band. So this filter is already present before the mixing operation and it is selecting our desired band. And we are talking about an image which may be present in this frequency region. Okay. So let's fix one channel here. For this corresponding channel, we are talking about an image which is at frequency FLO minus FIF. Since we already have a filter to select the band, we can say that this band select filter should completely attenuate this signal at the image frequency. And in such a scenario, we should not be facing any problem of the image. Oh, so this is partially true. So in reality, what happens when we are trying to design a band select filter, there are various trade-offs. So if you look at the antenna interface with our circuit, first block is this band select filter. Now this band select filter is handling much higher signal compared to our in-band signals because there can be out-of-band blockers, this signal at the image frequency itself can be pretty high without band select filter. So already this band select filter is trying to attenuate out of band signals as much possible, and definitely this attenuation is not infinite. It is attenuating it to some finite value so that at least these signals are reduced to levels which will not saturate or make the rest of the active blocks, for example, the variable gain amplifier and the ADC, to go into the nonlinear region. So the job of the band select filter is to bring down all the out of band signals into power levels which can be processed by the active circuitry in the receive chain. That is, so attenuate out of band signals to manageable level. Okay, so why not to go further and then completely kill the signals, anything out of the band? The reason is, if we target higher out of band attenuation, so as to give you a quick idea about what I'm talking. So let's say we design a filter which has this kind of roll-off. So this roll-off is going to decide how much of the out of band signals will be attenuated. Okay. Now, if I want a sharper roll-off, let's say like this, it turns out that it will also add more loss for the in-band signal. So this second filter has, I should say, higher out of band attenuation. This is achieved by increasing the order of filter. Increasing the order of filter means this filter now will be having more elements connected together. So once you have more elements connected together to give you higher order, each of those elements will also be adding its own loss. So this loss to overall will accumulate. So there is a very strong trade-off between how much of out of band attenuation needed and how much of in-band loss we are going to get. So there is a optimization problem here. So normally it is decided that we attenuate this out of band signal just to value low enough that it can be managed by the rest of the receive chain, so as to not incur excessive in-band loss the front end of the receiver. Okay, so this is fine, and especially for the band select filter, there is another requirement that they have to also handle very high power signals. Okay, because the signals will be out of band, their power levels are not going to be same as the signals which are in band. And by the way, this part, which is the loss which is added by such a filters when they are inserted in the signal chain, is also called as insertion loss. Okay, so we can see that the design of band select filter is not straightforward. We need to have this trade-off between the insertion loss and the out of band attenuation. Also, the filter needs to handle much higher power signals compared to the in-band signal. So it turns out that we just can't use any standard filter design. So there are some specialized filters, specialized technologies which are used to design this band select filter. So at a very lower frequency, and we will find that these surface acoustic wave filters are common, whereas if you exceed few gigahertz of frequencies, we need to use bulk acoustic wave filters. So here the filtering action makes use of this piezoelectric material, where the electrical signals is converted into mechanical domain, and then it is converted back into electrical domain, and so on. So overall, in a very compact form factor, we can achieve very high order of filter. Okay, so I hope this part is clear. Already this band select filter design is pretty challenging. Now let us talk about image reject filter. So once we know these image signals cannot be completely nullified by the band select filter, so we need to, because of this trade-off, we need to add another level of filtering, and this filter need not be as sharp as the band select filter, because we can see that the image signal is much farther from the signal band edge compared to the out of band signals. So out of band signals can be just next to the band edge, whereas this image signal will be at least FIF distance away from the LO, and the LO again will be at some distance away from the desired signal band. So you can say that image reject filter can itself be another band pass filter, much shallower roll off compared to band select filter. So we can cascade band select filter, another band pass filter, which we are calling as image reject filter or IRF. And this output has been given to mixer, then channel select filter. Now it's one more band pass filter. Then we are giving signal to VGA. And finally, the output is digitized. Okay. So this is how the current signal receive chain looks like. And the new block which we have added is this image reject filter. So we can already see that multiple filter stages are present in the circuitry. So each of these blocks, if it is not adding any power to the signal, what it does, it adds loss, so which we have already seen. And so this band select filter, if it is designed using these passive components, it will be adding its own loss. Each of these nodes also get some undesired signals getting added, and these are getting added as a artifact of all this electrical circuitry. So every time we insert an electrical block, it turns out that we are not only processing the signal, we are also adding some unknown signals to our own signal. And this is going to be added at every point. So on. Okay. So what we can do is, for example, if we just allow the signal to, which is appearing here, So this is the desired signal. This signal we just allow it to just pass it through all these blocks. What happens? Because of this loss being added by each of these filtering stages, our own signal may become weak. When the signal becomes weak and we are adding some unknown signals, then both of these signals together will be passing to the next block. And after some time, it may so happen that our desired signal may become comparable or even weaker than the combined strength of all these unknown signals being added. And when that happens, we will not be able to recover any information from the input signal. So this situation has to be improved, and this can be improved by making sure the signal is amplified to as high value as possible before any such signal corruption takes place. So we need to modify the receive chain by adding some active gain blocks as soon as possible. Okay, so ideally we would like to put some gain here itself, but the problem is here if you add any gain block, it needs to handle not only the receive signal but also very high power out of band interference. These interference can completely kill the performance of any gain block in the front end. So we need to protect those gain blocks from those high power interference that can be performed with the help of a band select filter. So just after the band select filter, we can add a gain block, and now after this, if there's some unknown signal being added, at least we know that we have amplified our desired signal to a higher value. So the corruption of the desired signal will be minimized. And once this gain has been added, now if we add one more filter, in our case this is the image reject filter, let each of these guys their own losses, but we know that whenever we are getting chance, we are inserting some gain in the stages so as to minimize the corruption of our desired signal. So this amplifier is not just any regular amplifier, especially the amplifier which is appearing as the first amplifying stage in the receive chain, also have to be designed such that the amount of this unknown signal which is being added is minimized. So this unknown signal is also called as noise. We'll look a little bit later about the details about what is noise, how we can at least quantify the effect of noise. This is being added everywhere. Okay. So when we are trying to amplify, we need to make sure such a block adds minimum amount of this undesired electrical noise. So this block is also called as low noise amplifier, or in short, LNA. Now we have added one more block in our receive chain, and this output of the image reject filter goes to mixer output goes to channel select filter, which is operating at a intermediate frequency. And now this output goes to VGA and the ADC. Okay. So here we can see almost complete picture of a received chain. And I hope you understand the reasoning behind inclusion of each of these building blocks in this receive chain. So with the help of band select filter, we are able to get rid of out of band interferers. Then a low noise amplifier has been added so as to reduce the impact of electrical noise in the overall signal quality. And after that, we have added an image reject filter so that it can minimize the effect of image once frequency down conversion is implemented with the help of this mixer. And finally, we are doing a channel selection in the analog domain with the help of channel select filter. And this selected signal is going to be amplified to bring the signal within the input dynamic range of the ADC. And finally, the ADC is going to digitize them. So if we see here in this architecture, we have an important design choice, and that design choice is about the choice of intermediate frequency. The intermediate frequency, as we have already studied, influences the design of image reject filter as well as decides the complexity of a channel select filter. So we will just look at this design choice briefly. To understand the design choice of intermediate frequency, let us look at the signal spectrum. Let's say this is the low frequency. And here is a channel which needs to be down converted for channel selection. In addition to that, we also have an image frequency and some signal at image frequency. And we all know the result of the down conversion. All of this are going to appear at the same frequency which is at FIF. Now, if we want to design the image reject filter, we can see that the image reject filter has to pass entire band by attenuating the image signal. Now, the spacing of the image frequency from the band edge is going to decide the roll-off for the image reject filter. IRF roll-off, I should say order, is reduced if the spacing increases, and that spacing directly depends on the IF frequency. Whereas if we look at the channel select filter has to pass only the channel, and to do this it needs to have a sharp roll-off to reject adjacent channels. So the channel offset is always fixed. So that is not going to change irrespective of the intermediate frequency. But if the intermediate frequency is at a higher frequency, is increased, then it turns out that we need to design a filter which again gives the same kind of attenuation in a very narrow frequency offset, but having an IF frequency which is higher. So to design such a filter, again we see that this filter is going to have a higher quality factor or higher roll-off, which in turn leads to increase in the order of the channel select filter. This is your channel select filter. Here the trade-off is CSF order increases with increase in IF. Here order increases with increase in IF, where as for the image reject filter, order is reduced if we increase FIF. So we have got two opposite trends, which is decided by choice of intermediate frequency. So based on what is feasible, the intermediate frequency is decided by the system architect to optimize the complexity in the design of channel select filter as well as image reject filter. In the current scenario, since the image and the desired signal both are present at the same frequency, in general it is just not possible to separate these two signals. So as to understand this phenomena a little bit more into the detail, what we will do is we'll take example of LO signal, try to see when it is mixing with signal which contains the desired signal as well as the image signal, how the spectrum looks like for two different cases. A cosine signal and process which we are going to analyze here as this input which contains our desired signal plus the image signal. Okay, and we are going to look at how this output looks like. So let me call this output as I of t. So in the time domain, not only, okay, just to add one more piece of information here, we are also assuming that there is a filtering which has been added after the mixing operation to get rid of those high frequency spurious contents. Okay, so if you remember, every time we are going to do this mixing, it not only gives rise to this low frequency component, it also gives rise to components at frequency FLO plus FRF and FLO plus FIM. So we will just assume that channel select filter has filtered out. So in the time domain, this can be represented as let me cos the LOT being multiplied by signal plus image, and this cos omega LOT, you all know, can be written as sum of two exponentials. This is for j omega LOT and e to the power minus j omega LOT divided by 2 multiplying with signal and image. Okay. So as to understand the behavior of this product, again what we are going to do is we will draw the spectrum. As we can see, it requires each of these complex exponentials to multiply with the signal in frequency domain, which is same as each the signals convolving with the signal and our desired signal and the image signal. So we can very easily see that the convolving means, in our case, just flip the spectrum and start moving this LO signal first, let's say on the right side. So we can see if we are moving on the right side, it is going to convolve with the positive signal component and the negative frequency side of the image signal. Whereas when we move on the left side, it is going to bring down the signal component at minus omega RF and the image component at omega IM. So we'll just draw the resulting spectrum. As we just saw, if we are moving towards the positive frequency, these two signals are going to first get down converted. Whereas when we are moving towards the left side, so the omega minus IF, so here it is omega IF, omega frequency at minus omega IF, we are going to get components from negative omega RF and positive omega IM. And we are right now not worried about those high frequency components because we are assuming there is a filter here which will only filter the low frequency component, okay, around omega IF. Fine. So we can directly write this output, which we have earlier denoted by I of t. So after passing through channel select filter, I of t, the way we can see here, each of these components have been now shifted to a lower frequency. So if you look at the signal has, as you can see, the same component but at a lower frequency. So this is, let's call as signal IF T. And if we look at the image side, so the image also has moved to Image also has moved to the lower frequency. This image component, which is now shifted to an higher frequency. Next, let us take a case where the halo, instead of being a cosine function, let's say it's a sine function. Mixing with sine omega LOT. Sine omega LOT being multiplied signal image and we all know sine omega LOT minus j to the power j omega LOT plus j to the power minus j omega LOT divided by 2. This is getting multiplied with signal and image. Okay. And let's call this output, which finally going to be filtered by the channel select filter, as Q of t. So next step, we are going to look at the spectrum of this various signals to understand how the spectrum of Q of t looks like. So compared to the cos omega LOT case, here our complex exponentials have different coefficient. It is minus j by 2 and plus j by 2 compared to 1 by 2 in the cos omega LOT case. So if we assume that these are all real components, then plus minus j will be appearing like this. So just to simplify the diagram here, what I will do, I will draw the LO again along the same y-axis, but I will just multiply with this minus j to show that this signal actually is purely imaginary, and which is minus 90 degrees shifted compared to the real signal. And this is appearing at omega LO. Similarly, if I check the signal which is at minus omega LO, it is getting multiplied by ST. Okay, now we will perform the same convolution as we did earlier. First, flip the spectrum to you how the convolution is going to down convert the two signals. So we are going to see the convolution. So first, the sine omega LO signal has been flipped along the y-axis, and now if we move on the right side, we can easily see that the positive frequency of the signal is going to multiply with plus j, whereas negative frequency component of image is going to multiply with minus j. Okay, so let me keep it down here. So it means this positive frequency is getting multiplied with plus j. Let me plus j multiplication in this manner. Negative component of image is getting multiplied by minus j. So just to emphasize that this is multiplied by minus j and drawing it below the x-axis. Okay, this is all happening at omega IF. Similarly, if we move on the left side, we can see that the positive frequency component of image is multiplied with plus j, whereas negative frequency component of desired signal is getting multiplied with minus j. So the desired signal is getting multiplied by minus j, whereas image is getting multiplied by plus j. And we can very easily see distinct spectrum as compared to when we are multiplying with cos of omega LOT. Okay, so as to write the product after filtering by channel check filter, you can see that the signal component, so the signal component is again appearing at the IF frequency, but now it is getting multiplied by plus j and minus j. So it is same as, I call it as Q of t. It is same as the signal which was at the IF frequency as the earlier. Okay, but with the positive and negative frequency components getting multiplied by plus and minus j respectively. Similarly, the image is also getting multiplied by minus j and plus j respectively. Okay, so if we look at the frequency domain, we can see that it is same as the frequency domain counterpart we had earlier, but depending on the constituents of the signal, whether it is having positive or negative frequency, we are multiplying with, this case, either plus j or minus j. So this can be mathematically shown with the help of the sin function. Sin function is, okay, so this is the function we are using in our expression. Similarly, we can write the image signal to be same as the image signal which we got in the case of cos omega LOT, but now it is being multiplied by minus j into the sin function of omega. So this is a very important conclusion, and we can also see that depending on which component is higher or lower with respect to the LO, we are getting appropriate polarity of this j here. So this operation where signal is either multiplied by plus j or minus j depending on the polarity of the frequency component is also called as Hilbert transform. So if you take a signal and you apply Hilbert transform, it multiplies the signal with either minus j or plus j. depending on the polarity of the frequency, right? I of omega, frequency domain. So it was just bringing down the frequency of desired signal and image to IF. Whereas if we look at the Q of omega, which is a result of mixing with sine of omega LOT and then passing the signals to channel select filter, it as we can see here, it applies a negative Hilbert transform on that desired signal, whereas a positive Hilbert transform on the image signal. So I can write it as negative Hilbert transform, the desired signal, and a positive Hilbert transform of image signal. This is an important distinction. Now we can see that even though the down converted signal and the image component both have the same frequency, but depending on whether it was multiplied by either cos omega LOT or sin omega LOT, there will be a difference in the polarity of this transform. Okay, or there won't be any transform if it is multiplied by cos omega LOT. And from this definition of the Hilbert transform, we can easily see that if we apply the Hilbert transform 2 times, or if we keep shift the signal by one more time minus 90 degree, then we are going to get a negative of the signal which we started with. This is the concept which is utilized to separate the signal from the image, even though they occupy the same frequency. So what we do is we apply one more time Hilbert transform on the Q of omega. So if I apply Hilbert transform Q of omega, it gives rise to same signal which we started with. Whereas it negates the image component. This gives rise to a signal component at IF frequency minus the image component at IF frequency. So now we can see that if we have access to I of omega and then we take Q of omega and pass it through a Hilbert transform, we get 2 equations, and in these 2 equations, if we just add them together, we can get rid of the image and we will be only left with a signal component. And if I have to show this operation, it's a diagram. So what we are doing is RF signal we are multiplying with cos omega LOT. Parallel, we are also multiplying with sine of omega LOT, RF input signal. And both of them are passed through channel select filter. This is your I of t or I of omega, Q of omega. Now this Q of omega is again passed through Hilbert transform This final output of the two paths are then added together to get our desired signal at IF frequency. The architecture which implement this down conversion with the help of cos as well as sin omega LOT, and later on cancel the image with the help of one more Hilbert transform. It's called as image reject receivers. Easily see that depending on how accurately these two paths are matched, we can get very high level of image rejection. One way to implement this second Hilbert transform is with the help of simple RC filter. So I will directly show you the architecture which is commonly used. We know that with a simple first order RC filter, we cannot get a 90-degree. So what is done is we try to obtain relative phase shift of 90 degree between the two paths by getting a minus 45 in one path and a plus 45 in another path. So it's done by adding a RC filter, which is such that this FIF is equal to 1 by 2 pi RC. So at this, such a filter is going to give a phase shift of minus 45 degree here. Okay. Minus 45 degree. Similarly, we can implement a CR filter where again we choose the same values of capacitance and resistance. This will give plus 45 degree phase shift, where this will give minus 45 degree phase shift. So overall, we get a relative phase shift of minus 90 degree. And the final output, once we add together, will only have signal component. This architecture, specific way to implement the 90 degree phase shift between I and Q paths, is also called as Hartley architecture. And this is really a practical way to realize this image reject receiver. One issue we can already see that is these filters will have a very narrow band in which they will provide this equal magnitude as well as 90 degree phase shift. Where if you just look at the phase shift, definitely these two paths will always be having a 90 degree phase shift across a wide band, but the magnitudes are not going to be matched. They will be matched only at the pole frequency of these two filters. There is another approach to introduce 90 degree phase shift in the two paths and then add the signal to get rid of the image component, and that is by implementing the phase shift in the digital domain. So once the signals have been down converted to intermediate frequency, what we can do is we can digitize each of these signals separately. For digitization, 90 degree phase shift can be implemented in the digital domain. Benefit of this architecture is in the implementation of the 90 degree phase shift, which can be implemented in a much more accurate manner as compared to the 90 degree phase shift we were implementing in the analog domain. So this architecture is also very popular, where the final image rejection is achieved in digital domain. This architecture requires two ADCs, and as we have we can see that there are two paths for I and Q, and both the paths have to be tightly matched for complete image rejection.